It's quite a hike from Australia to Ireland, but it's definitely worth it, and I've had a great time already. Yesterday I went down a great pub, and someone there told me about the mountain that Mark mentioned and promised that if I climb it 3 times, I'll go straight to heaven. Now, I'm not sure whether that was a promise or a warning, to be honest. It's slightly ambiguous way of putting things. Anyway, let's get on with the talk. So, I'm going to start off with a few little provocative things. I'm hoping just to kickstart the discussion as much as possible. Talk about the long, dark tea time of physics, with the joke, you know, Douglas Adams. Now, look at thermodynamics of clocks, classical, quantum. And a quick glance at a non-periodic clock, a thermal clock. It's a bit like radiocarbon dating, except instead of just decaying, it's also really excited. And I'll finish with Rebecca Cummings' thermal time hypothesis. And so philosophical musics, because I see there's some philosophy on the agenda. Isn't there? There is. Good. Okay. So let's ask this first question. What do we measure when we measure time? People often say clocks measure time, but it's a little bit ambiguous. And back in 1911, as Mark put this really well, he said, we can eliminate time from every law of nature by putting in its place a phenomenon dependent on the Earth's angle of rotation. So if you more things than physically, then time is the representability of any phenomenon as a function of any other one. So here is a hint that the essence of time is purely relational, somewhat like temperature in thermodynamics. Carl Rovelli put it very clearly. In fact, anyone who teaches general relativity would make this claim very strongly. But the fundamental equations do not include time. He goes on to basically what clocks measure is change, which introduces yet another curly subject into the discussion. Time and change. It's not entirely clear that they're the same thing, and whether one is more primary than the other, but certainly things do seem to change. And he then goes on to point out that all of this does not alter the fact that the world is a ceaseless process of change, and what we actually do is measure one thing and simultaneously measure another and compare them in a relational way. I'll make that a bit clearer now. But before I do that, let me put up this slightly provocative statement, and that is, in physics, we're so used to studying it with little t inserted all over the place that we forget, of course, that that's just a real parameterization and has no actual physical content. It's just a convenient way of representing the laws which govern correlations between changing phenomena. I'll come back to that a little bit. But let me give an example. Here's a simple oscillating system, a mass on the end of a spring, and I've got a laser there that records when it is at some particular point in its trajectory, such that when the laser is occluded from the little photodetector, a bell goes off. And all I'm going to do is have a counter, there represented as a counter of mod 12, but it could be any counter, counter. It's hard to see, but on the right is the count 1, 2, 3, 4, 5, 6, 7, 8, 9, and I record a 0 or 1 whenever the ding goes off at any particular count. And that's it. That's really all there is to time in this system. There's no units. There's just phenomenon, two phenomena. I have to assume that in some sense the clock is not strongly interacting with the laser and everything else. They should be independent. And implicitly all this is a notion of an observer or an agent sitting outside watching these correlations. So in other words, and I should also point out that we really have to be a bit careful about the local environment of the clock. So one thing to stress is this makes clocks purely local and time a purely local phenomenon, which we already understand from general relativity. And also you need to make sure you understand the thermodynamic environment of the clock, particularly in the case of gravitational field and the Tolman relations. So in this way of looking at it, a clock is just a count. And a clock is just a device to coordinate coincidences in this picture, local coincidences. So, I don't know whether this is going to work. Perhaps I'll just skip it and come back to it later. So here's how we would write the expression for these coincidences. It's a table or a function. It's an integer value function. Or in the way I've written it, it's a binary value function, but I put it right the other way, where n is just an integer. But of course, there are various ways of writing that. There's always, if there's some phenomenon that repeats regularly, then this function, there exists some integer a, where this relationship is purely periodic. So the same phenomenon repeats at count 1, count 4, count 8, and so on. As I'll explain the rest of the talk, there are no perfect clocks. The simplest way to incorporate that into this picture is making a modular function that's also random. by including n mod big N and make n a random integer with mean of A, we now make the mean period of the clock, and some fluctuations, which means that the count will fluctuate. Typically, we would define a count function as just summing up all these binary numbers. Sometimes it's 0, sometimes it's 1, so we just count them all up, and we'll get a kind of step function which accumulates a count in this picture. Now, where little t enters the picture is a parametric representation of this function. It's not obvious that this is always possible because these are integer or binary valued functions, but there are theorems in integer valued functions that tell you that this is always possible. And now t is a real parameter in this picture. And I'm stressing here, although you might want to argue this, that it has no physical significance. It's only the relation of coincidences between physical events, bell going off, count on the clock, that actually tells us the physical content of change. So in this picture, time is purely relational. Here's a way to do it. I could write n of t as simply the integer part of this real parameter, t, and I could write the count function as the integer part of t over a, where a is the period of this function. So we just see it stepping up. This is in the deterministic case. So there's always a simple way to write these integer value functions in terms of a real parameter. And even make them stochastic, should you wish to do so. Okay, so this stresses that what matters is this relation between counters and changing phenomenon. And it refers to space-time events, not coordinate frames, not some arbitrary position frame for the clock and some arbitrary t for the clock, but just local coincidences. And in that sense, it's coordinate-free. And I'll even go so far as to say, although you may want to argue this, that all space-time events that define space-time are necessarily the results of measurements. Now, of course, Einstein did say that because he thought things were really, he believed strongly that the world was really out there, and when we observe it, we see it as it is. But in quantum mechanics, it's difficult to maintain that perspective. So I will take the view that all space-time events refer to the outcomes of physical measurements in a quantum case. Now, of course, the real parameterization varies a lot depending on the physics. In Newtonian physics, it was assumed to be universal for all local clocks. In special relativity, it depends on the relative motion of the clock and the event. And in general relativity, it depends on the local gravitational field at the clock and the event. But I won't go into those details. Let me move on now to talk about the thermodynamics of the sorts of clocks that we build in the lab, or buy, if you wish. And the key point to emphasize here is that all clocks, both classical and quantum, are irreversible systems pushed away from thermal equilibrium. There are a couple of ways you can push a system away from thermal equilibrium. You can do work on it, or you can reduce its entropy by making measurements upon it and talking about the conditional dynamics of the clock. Both push the system away from thermodynamic equilibrium. I'll come back to that in a little bit more detail. And both increase the free energy of the clock, pushing it away from zero. So you can do work or you can make measurements. And some of this I discussed a while back in this review paper, and a lot of it appears elsewhere in the literature going back decades. So here's a really simple clock. I wanted to start with the simplest possible clock that everybody who studies quantum mechanics knows only too well, and that's the infinite square well. So this is just a particle bouncing initially elastically between two impenetrable walls. And so on the left there you see the conservative dynamics. Its momentum is conserved because it's just kinetic energy between the walls. When it hits a wall, its momentum is reversed, it goes back the other way, and this repeats over and over again. If, however, and of course you would just define the period as L over 2 times the modulus of the momentum. So it's a nonlinear oscillator insofar as if the period depends on the energy. The higher the kinetic energy, the bigger the momentum, the shorter the period. So it's not simple. It's not simple and it's not harmonic. As we'll see in a minute, it's got a square wave or a triangle wave. On the right is what happens in the presence of dissipation. So let's imagine these collisions are inelastic and a little bit of energy is lost in each collision with the wall. And then you see it will just gradually wind down and stop in the classical case as the momentum decreases. So the problem with the clock is dealing with that kind of friction. If I had a perfectly closed system that kept repeating like that, everything would be fine. But typically, closed systems are impossible. You get closer and closer to them, and generally you have to deal with dissipation. So how do you fix that? Well, first of all, let's just look at the statistical mechanics of that. We only really have to look at the momentum map, just look at this as a discrete map from just before one collision to just before the next collision. And there's this parameter eta, there's a sign change because it's reflected and loses a little bit of momentum at each collision. But in order to preserve thermodynamic equilibrium in the long run, I need to add some noise. And this is just the fluctuation dissipation theorem in a discrete form. And you can easily see that the variance of that Gaussian mean zero random process is just proportional to the temperature of the walls into which the energy is being dissipated in this system. Actually, this turns out to be exactly, or very closely related to the logistic map. And it's relatively easy now to add a driving term. And obviously I've added a driving term here, which is f into 1 minus p squared, to make it look as close as the logistic map as possible. Might be a bit tricky to arrange. I'll give you an example in a minute about how to get close to it. But you can see as you increase the driving towards f, ignoring the noise, this system undergoes a period 1 bifurcation from a fixed point to a period 1 point. Then the period doubles again and very quickly cascades into chaos as you drive up f. So clearly we don't want a chaotic clock, so we'll operate with f around 0.5 to make this thing work. So there's damping, and there's driving, and there's noise. And we need a counter. And in the classical case, we just read up the momentum, and that's as good as reading up the period. So here's some examples. There's a classical stochastic simulation of the mean momentum. You can see it's just got this sort of fluctuating square wave structure. It's trying to decay, but there's some pumping mechanism. Over there are plotted periods, and you can see they're stochastic. And then I'll just run through a large sample of those to look at the histogram of the periods. And you'll see this characteristic structure, a slightly asymmetric distribution around the mean. I'll come back to that a few times. So that's a really, really simple classical clock. The trick is how to describe it quantum-mechanically. Well, to do that, I'll move to a continuous picture. So I'll just put a continuous potential to represent the square wave, which is a little bit, mathematically homological. It's just this basically two sigmoidal functions back to back. You can solve the classical equations of motion, and you see the momentum is the square wave in the absence of dissipation, and the displacement is a triangle wave in that form, which is what you expect. And now you can include dissipation, resulting from inelastic collisions with the walls. There's various ways to model this. Clearly, the dissipation occurs at a collision with the wall. It's not sort of frictional damping all the way across, so you've got to be really careful about how you include it, but there's a simple way to do it. You just write down Hamilton's equations. Minus v prime x is the conservative dynamics, minus gamma p3 double prime x is the position-dependent frictional damping of the system, so that it only suffers energy loss at the walls. And then I'm going to put in the pumping term, gamma, which depends on the momentum and the derivative of the sigmoidal function, which basically just gives a little kick as it passes through the origin in the position space of the clock. It's a momentum-dependent forcing term, and you might wonder a little bit about that, but in fact, many clocks have that feature. The pendulum clock, for example, has exactly that feature. The kicks provided by the escapement mechanism depend on the displacement and the angular momentum of the pendulum. But anyway, when you do all that, you quickly discover it has this very nice limit cycle. You can't overdo it, of course. If you drive it too hard, all sorts of complications, period doubling sequences occur. But the key point is this is a limit cycle. So by a limit cycle, I mean this is a dissipated structure. That is, if I could push the system away from the limit cycle, it will very quickly move back onto the limit cycle. If I started well off the limit cycle, but in the so-called basin of attraction of the limit cycle, it will move on to the limit cycle. But it's a dissipated structure. It's going to dissipate energy. And I'm also doing work on it through the kicking mechanism. And in fact, the limit cycle, well, there's an example of a clock signal where I just take 1/2 plus 1 plus the sign of the displacement just to get a nice signal out the back of the cap. And as I said, the limit cycle forms when the work done on a cycle is exactly matched to the energy dissipated on the cycle. But as I'll stress, in the statistical sense, the energy dissipated fluctuates from one cycle to the next, therefore the work done fluctuates from one cycle to the next, therefore the period fluctuates from one cycle to the next. And you can see the period fluctuating there. In fact, if you do a histogram and do a best match to a distribution, I'll come back a little bit later, it's the inverse Gaussian distribution or Weyl distribution. You again see this sort of asymmetric structure, and it gets sharper and sharper as the noise gets smaller and smaller. But what I want to emphasize here is that unlike in ordinary statistical mechanics where to decrease the noise, you would have to cool the system. On a classical limit cycle like this, to decrease the noise, you just drive it harder and make the limit cycle bigger. And this is the key feature of limit cycles and why they're important for clocks. And that is the noise on the limit cycle is controllable by the strength of the driving. And I'll come back to that theme a number of times. So let me just summarize. On each cycle, work done by the drive equals the energy dissipated. But each of those is a fluctuating quantity. And the larger the limit cycle, the greater the power dissipated. And furthermore, the noise gets smaller as you drive it. So let me just show you a typical picture here. The key feature of all these sorts of clocks, from the pendulum clock to the square well to almost the quartz clocks, which basically have a little amplifier in there based on a current running as a comparator, plus a piezoelectric oscillator, they all work on limit cycles. You don't have to have a limit cycle to run a clock, and I'll describe much later in the talk, which is a non-limit cycle. But typically they're on a limit cycle. And the reason being is it's stable under noise. The system, if it's pushed off a little bit, will move back on the limit cycle. Now, when mathematicians study these things, they introduce something called the phase function. And this is a fairly complex discussion called phase unfolding of trying to represent the dynamics on the limit cycle purely with a phase that varies between 0 and 2 pi. And clearly, if the limit cycle is complicated, that won't be a very simple function of time. It will be slow in some, for some time and fast in others. For example, some very spiking type clocks will be slow and fast and slow and fast. But there's always a phase theta which varies around the limit cycle. And that's essentially our clock. It is folded on 2 pi, and we just count the number of cycles somehow. I'll describe a little bit more about counters. To make a clock which is counting, which ultimately goes back to this relational picture of clocks coordinating both instances. So the generic way of thinking about a limit cycle is in terms of something called the normal form for Hopf bifurcation. So basically these equations here, so you'll see there's a term x dot minus omega y and y dot plus omega x, so that's like a harmonic oscillator term there. There's also some gain terms, so this is mu as an amplification term, x dot mu x, y dot mu y. Then I have a term which looks like a damping term that depends upon the energy, x squared plus y squared. So there's a minus sign there and a minus sign there. So this is like energy dependent damping. And then there's some, well actually the way I've done here is energy dependent frequency, but you could also do energy dependent damping. And then there's some Gaussian white noise process sitting on the momentum equation required by the fluctuation dissipation theorem. Okay, so on the limit cycle, so in this case the limit cycle forms when x squared plus y squared, which is a 2 missing on there, x squared plus y squared equals mu. So the limit cycle is a circular radius square root of mu in the phase plane. And so on the limit cycle, I can write x as a cosine function of this phase angle, and y as a sine function of the phase angle. And then if you change the variables and be a little bit careful with the Ito calculus, you find that the phase satisfies this stochastic differential equation, which has omega, which is just the harmonic oscillator part of this, the noise term sigma, but the key is it's divided by mu, which is the size of the limit cycle. So the harder you drive it, the more amplification you put into the system, the slower is the rate of phase diffusion on the limit cycle, and therefore the better the clock should be. And there's a number of discussions of this. This is the clearest discussion I found by Emma Zara and Philip Holmes from Confidence on Decision and Control. But there are a number of reviews of this subject of phase unfolding. In general, it's pretty complicated, especially in higher dimensional systems. Okay, so now a couple of things. In many systems, you can control this normal form for the Hopf bifurcation. Obviously, this is some linearization close to where the limit cycle forms. In general, the omega will depend on many parameters in the actual dynamical system. So you can control the frequency of the clock to some extent by how you bias the physical system. And you can control the noise by controlling the degree of amplification or gain in this system or degree of nonlinearity. And there are two features which are very desirable in building the clock. Okay, so now let's focus in a little bit more carefully on the noise in the period. Let me just put this here so I can keep track of the time. I'm going to talk about first passage times, which I think Michael is going to talk more about this afternoon, and others probably as well. And it's this notion of one period of the clock is one cycle around the limit cycle. But as I stressed, the limit cycle forms when the work done equals the power dissipated, and both of those are random variables. Therefore, the time around the limit cycle should fluctuate. Nonetheless, it always goes through 2 pi. And sometimes it takes a little bit quicker because the noise gets you there a little bit faster. Sometimes the period's a little bit longer than that because the noise gets you through 2 pi a little bit more quickly. And so the period necessarily fluctuates on the limit cycle. So what we really care about, starting somewhere on that phase unfolding, what's the distribution of the first passage time, the time for it to take to go through 2 pi for the first time. Of course, it's going to keep going through 2 pi, but let's just concentrate on the first passage time. And that will give us some handle on the statistics of the clock. Well, it turns out this is a classic problem in statistics. It's called the inverse Gaussian because it's sort of like the inverse to Brownian motion. In Brownian motion, you say, how far does the thing get in a given time? Here we're saying, what's the distribution of times for it to get through a certain distance, 2 pi. So it's the inverse Gaussian or Weyl distribution. It's a 2-parameter distribution. It depends on a mean, alpha, for the period, and a parameter lambda, called the spread parameter, which is connected to the fluctuations in the period. And in the standard way of writing it, the mean is alpha, and the spread parameter determines the variance in the first passage times by alpha cubed on lambda. So this Weyl distribution won't always apply, and it will only apply approximately in many cases, but it gives a good way of understanding how to parameterize fluctuations in a clock on a limit cycle. So in the case of a normal form, you can plug in the expressions for the period, which is omega, and the variance, and it turns out to depend on 1 over mu, which remember is the gain or the amplification rate on the limit cycle, and you can see as you make that really big, the fluctuations in the period get smaller and smaller. Now, of course, if you drive it harder and harder, you'll make the limit cycle bigger and bigger. It's going to start dissipating more and more energy. So we see this connection between good clocks and power dissipated. And this has been discussed by lots of people, including this very elegant table, which I first noticed in this whole subject of stochastic clocks by Paul Berkeley and others, but many people have since shown how this works. But of course, this is all classical. This original method was quantum. So, now let me just make a few more points. Here's a plot of the inverse Gaussian or Weyl distribution with fixing the mean at 1 and gradually changing the spread parameter. So as the noise decreases, the spread parameter increases, and it gets more and more sharply peaked on the mean period of 1. Now there's another very important feature of the Weyl distribution, that is called the principle of divisibility. So let me take a little bit of time to explain this. So imagine we have some period t with a Weyl distribution with mean alpha and spread parameter lambda. Then there exists n pieces of independent identically distributed random variables, t1, t2, such that they all add up to big T. But each of these random variables itself forms a Weyl distribution with a mean of alpha on n and a spread parameter of lambda on n. This is a very important feature of the Weyl distribution. Now that makes life pretty easy when we regard each tk in a ticking clock is going to be independent under this Weyl distribution. Now we can start to compare different clocks by looking at the different histories of this ticking. So the stochastic history of a particular clock will be some total count n and a list of these periods. I stressed at the beginning, the actual clock, all that matters is the count, but if we have a parametration of time in the experiment, which we typically do, because we understand the physical equations of motion and are determining it, we also have a list of these periods that are just a bunch of times taken for it to go through 2 pi. Then each of those is distributed by a Weyl distribution with a spread of n alpha, a mean of n alpha and a mean of n lambda for this total count t. The interesting consequences of that is that the total elapsed time, parametric time in this thing, is just the sum of all these periods tk. And then you can show the uncertainty, The mean is just n times alpha. That's what the property of divisibility means. And the variance goes n squared alpha cubed on lambda. So the signal to noise ratio is the mean over the standard deviation is the square root of lambda on alpha, independent of n. So this highly idealized plot that is truly described by a Bell distribution. And that's a nice feature. Even better, we can now start to think about comparing two plots, which is what you typically do if you wanted to look at an Allen deviation or something like that to two clock signals. So we have two independent clocks with the same values of alpha and lambda, so they're identical insofar as their construction leads to the same parameters for the Bell distribution. And we can then regard clock A as the relational clock for coordinating the tick events in clock B. So now our events are simply ticks of the clock, but I'm going to write one as the clock and one as the actual event that I'm coordinating. It doesn't matter, it's perfectly symmetrical. And I can say, how good is it? So the problem is that when A records a count of n, the number of events that n recorded in clock B is not necessarily the same because they have fluctuating periods. So these are random variables. But I can compute an error function for a particular trial as just 1 minus m on n squared. If the clocks truly ticked exactly the same number of ticks, this would be 0. And now I can use the Bell distribution to compute the mean value of that quantity. And it turns out that alpha equals 1, just to fix the units, be 1 over the spread parameter. So as the clock gets better and better and better, the spread parameter gets bigger and bigger and bigger, and the mean error between these two clocks gets really, really small. And so this enables you to simply plot a way to compare two clocks chosen here so that we can see that as the noise gets less and less and less, the spread parameter gets bigger. The two clocks are more likely to agree than not. And so that's for two identical clocks. In general, of course, you won't have identical clocks. It's very difficult in physics to build identical machines. And so the spread parameters and the mean parameters will differ for each clock, but you can take that into account as well. All right, enough said about classical clocks. Let me now move on to what happens in the quantum case, which of course is a bit more challenging because we have to explicitly take account of a couple of important features. First of all, in order to talk about quantum clocks, we're explicitly talking about very low temperature. So we're in a regime where you're outside of the standard fluctuation dissipation theorem and typical linear response. You're in a regime where everything is dominated by quantum noise. They're still irreversible insofar as they are driven damped systems. But now the irreversibility is coming from, say, for example, quantum tunneling, or from spontaneous emission, or from, in the case of the double well, coupling to quantum fluctuations in the vibrational degrees of freedom in the walls. Or you could imagine building a square well by putting two cannonballs on the end of strings as big pendula and just letting the particle bounce backwards and forwards between them. If you quantize that, it's clearly just coupling this bouncing particle to vibrational degrees of freedom, which at zero temperature will be 0 point fluctuations in the degrees of freedom that carry away momentum at each collision. But very importantly now, we have to be quite explicit about what it is we measure. So, unlike in the classical case where we could just pretend that it always had a momentum regardless of whether we looked at it or not, here to get a clock signal we're going to have to measure the right thing, otherwise we won't actually get a signal that oscillates at all. And so this is a somewhat additional feature one has to be careful about in the quantum description. So I'll try and go as far as I can on the continuous square well case. It turns out to be a little bit tricky, but you can get it some way because here you're going to, because the infinite square well has an infinite number of bound states, which is a little unrealistic. And so now it's a question of how many bound states to include in the simulation. But we know how to describe, at the very least, dissipation and certainly continuous measurement. So let's consider continuous measurement of the position of the particle bouncing backwards and forwards in the square well. We know in that case that it will tend to decohere the system in the position basis. That is, it will tend to become diagonalized in the position basis, and simultaneously that will add noise to the momentum will diffuse. So the measurement will necessarily cause noise in the momentum. But when we measure it, we have to take into account the fact that we are acquiring information about the system. And the measurement record is a real classical record. It's a classical stochastic process, which is sitting there as numbers on your computer. And whatever happens in the future has to at least be consistent with everything you saw in the past. And that leads to this nonlinear operation acting here with a beam of diffusive noise where hx is nonlinear because you can see it depends upon the instantaneous state rho through this here. In the formalism, this is just coming about through normalization of probabilities in each time step dt as the measurement record proceeds. So that's what it looks like from the point of view of the measured quantum system. What you actually see, of course, is a measurement current. What you actually see is some classical stochastic process, which in the scale I'm using here, the scaling I'm using, depends upon the mean, conditional mean of the position. The conditional mean means the trace of x over the solution to this equation. So the two are kind of tied together because the conditional mean is also coming in here. So these are kind of tied together. But this current is noisy, and you'll notice that the noise gets smaller as this rate gamma gets bigger. So gamma is clearly something about the measurement rate, because if the gamma is really big, it becomes rapidly diagonalized in the position basis, which is what you would expect for a good measurement, and simultaneously add a lot of noise to the momentum. But that also corresponds to having less noise in the observed signal. So this is what's going to come out the end of your clock, this measurement signal. Now, if you measure the energy, well, this will look very different. You have a double commutator with the energy up here, you have something here. We tend to drive the system towards energy eigenstates, which is not very good from the point of view of the clock, because energy eigenstates by definition are stationary states. You don't measure the energy. You could also measure the momentum, that would be fine, but I've just done the position here just for the sake of something to do. So here's an initial state. Choose it to be well localized somewhere on one side of the double well. I've just put some truncated exponential distribution here. Unfortunately, left out the normalization, but it's in the numerics. And I made A really low so I could truncate it n equals 3 so I could do the simulation yesterday on my laptop. Here's what the conditional mean of position looks like for this system. You can see it looks pretty periodic, which is not surprising. But it also fluctuates quite a bit. It's a little bit difficult to see the phase fluctuations. There. But let me stress one interesting feature of this clock. The only way in which irreversibility is entering this thing at the moment in this simulation is purely Hamiltonian dynamics plus measurement. There's nothing else. There's no damping and there's no driving. It's strange from the point of view of the clock. But it's enough to get a signal out like this. It's a bit noisy, but it doesn't decay. It fluctuates a bit. So in a sense, this is a purely information-driven clock. It's an example of a clock in which the measurement itself is pushing the system away from thermodynamic equilibrium and driving it to this conditional state, which enables you to track the oscillations. That's the kind of information-driven clock. And the FQXI supported part of this project in their information as fuel program. I think some of you are part of that program as well. If you average over all the noise, you get what you expect. The position, in this case, because I started it really close to one wall and truncated the expansion, just settles down to be sitting more on the left of the well than the right. So it's not, that's not a clock. You only see the clock in the conditional dynamics. Okay. So there are a couple of points to take away from that. To make this a proper clock, I really have to add damping. All I've done is measurement. And I need to add gain. And I need to include the measurement. I'll show you how to do that. So there's a very well-known example where all of that is done fairly easily, and that's the laser. And a laser is a quantum clock if you add a counter. And much of what I'm discussing here was pointed out by Howard Weissman many, many years ago. But of course, people who make clocks know very well that a laser is a clock, because that's where they start, either with a laser or a maser when they're making the clock. So let me just describe each of those features: damping, gain, and measurement in the case of a laser. First of all, it's a thermodynamic autonomous system because it operates between two temperature reservoirs, one hot and one cold, because the objective of the pumping mechanism is to create a population difference between the lasing transitions. So the population, the ratio of the probabilities in the two lasing transitions is not thermal equilibrium, because in that case it'd be more likely found in the ground state than the excited state. You need these two reservoirs in order to drive a population inversion in the system, so that the Boltzmann factors change around, which looks like a negative temperature in the case of a laser. So that fact is clear. Then various models you can introduce, you can put in the atoms, you can put in the cavity, you can put everything you like, but there's a simple way to adiabatically eliminate all the matter and just get this very simple equation, which I put from Howard Weissman's work, where there's some dissipative term, over here due to spontaneous emission. So this is basically corresponding to cross-on distributed photon emissions out of the end of the cavity. Then there's a gain term, which in place of A corresponding to losing photons has an A dagger and a gain. So this would add photons to the cavity. But it's highly nonlinear in that there's this gain suppression term here, which enables the gain to turn off if the excitation gets too large. Because clearly, if you just had linear damping and linear gain, as soon as the linear gain exceeds the linear damping, everything explodes. Well, usually nothing explodes in the physics lab, at least not with dominant control. Anyway, some other nonlinearity will switch on and stop the system from entering that unstable regime. And here it's entering through this gain suppression, through this function to the -1. This A operator is to the -1, but it's more easily defined directly in terms of this anti-quantitative. So the key physics parameter is that G is the small signal gain, NS is the saturation photon number, which is telling you roughly where this thing begins to switch off the gain, and cavity kappa is the cavity decay rate. So there's loss, gain, and nonlinear saturation of the gain. If you just write down the mean field dynamics of that, it turns out to look very much like the Van der Pol oscillator. In fact, it is the Van der Pol oscillator in some rotating frame. And it looks very much like this. It has a fixed point, which corresponds, well, in fact, there are two fixed points. There's one below threshold where the mean field is 0, and there's one above threshold where the mean intensity is given by the gain times the saturation photon number divided by kappa. And that's well above threshold, G much bigger than kappa. So it has this bifurcation from average zero field to non-zero average intensity. And in fact, that corresponds to a limit cycle. If you just plot this thing, you can see the limit cycle is actually forming at that radius in this system. So a laser semi-classically is indeed a plot on a limit cycle. As we know, you can write down the photon number distribution. I'll just quickly go through this. It's all pretty standard. You can solve that in the steady state, and you get the usual cross-on distribution, where it's just some number to the n over n factorial, essentially corrected a little bit by the saturation photon number. Below threshold, it's essentially a thermal-like state, just looks like a light bulb. But above threshold, it's got this limit cycle with a Poisson distribution. And above threshold, it has a Poisson distribution where the mean, oh, I should have emphasized something there. So the key question, and I should emphasize, of course, that we already know in the laser there's going to be some line width associated with phase fluctuations on the limit cycle. So the limit cycle, if you solve the steady state equations for the laser, you'll get an annulus on the limit cycle. But we know, in fact, in the stochastic realization, as I'll describe in a minute, it should slowly diffuse on that limit cycle. The diffusion rate will just be the line width of the laser, which is just the shallow Towns line width. So in this case, we see the phase diffusion rate of the limit cycle is the shallow Towns line width, which is indeed inversely proportional to that. Now, what should you measure? Well, the first thing you won't want to measure is the photon counting. First of all, in a real laser, the photons are coming so thick and fast, it's going to be very hard to get a detector to resolve individual counts. They could be coming at a rate of 10 to the 14th per second, and that's well above gigahertz rates for even the very best photon detectors. But furthermore, because it's Poisson distribution, they all look pretty regular, and it looks just like a fluctuating constant intensity. It doesn't look much like a clock signal, so you don't want to measure that. So what you measure is some phase-dependent quantity, which typically means homodyne or heterodyne detection. You measure the electric field of the light exiting the cavity. You measure its amplitude, and then you can pick up the fact that there's a clock signal. So this is described in these two papers by Howard many years ago. And the basic point is, on the limit cycle, the master equation that describes the laser looks purely diffusive. It conserves energy, so an equation like this, which is basically a double commutative with respect to photon number, will not change the photon number distribution, so it will always be Poisson. It'll always have the same steady state photon number distribution above threshold. But as soon as you try to localize it on the limit cycle, this will immediately cause phase diffusion. And secondly, the phase diffusion rate goes as kappa over 2n bar, where n bar is the mean number of photons in the cavity. And as the dissipation rate from the cavity is kappa n bar, this tells you that the phase diffusion rate gets smaller as you make the dissipation bigger and bigger, exactly what we expect on a limit cycle. but in this case it's the quantum case. So you would measure, say, the amplitude of the field by time detection to get a clock signal, and straight away we get the same sort of classical stochastic process where it depends upon the conditional mean of the average field inside the cavity and some complex value noise process in this case, because in heterodyne detection it's equivalent to a simultaneous measurement of position and momentum, essentially the in phase and out phase quantities of the field inside the cavity. And that will carry the entire history of the clock. Likewise, there's a conditional quantum dynamics governing the system. Again, it's got this nonlinear operator here corresponding to making the future observations consistent with the past observations, and so you solve these two things together to get the actual clock signal. So I won't go into too much more detail on that. I think the laser is a sufficiently well-known example for that to sort of fix the key idea that in the quantum case, the measurement must be explicitly included to extract the clock signal. Now, there are many ways to measure it here. I'll just consider weak continuous time measurements. You need to do that if you want. You could consider impulsive measurements, saying an ion trap clock. That's typically what you do. An ion trap clock, you might also use resonance fluorescence showing. There are many different ways to do the measurement, but you've got to find the right measurement to actually get a clock signal out of the thing. Well above threshold, when we put in the phase diffusion, we now have this conditional measurement and the phase diffusion sitting on top of it. And you get, if you imagine writing in that case, the conditional distribution as a distribution over coherent states, which turns out to be a very good approximation to solving the stochastic master equation, then write alpha in terms of amplitude and phase, and you quickly see that this obeys a very simple diffusive stochastic differential equation where gamma is again the Charlotte-Towns line with showing the diffusion rate gets smaller as you drive the laser harder, higher and higher above the threshold. Okay. Now, a laser, I said it's a clock, but it's not much of a clock until you add a counter. And most of the technology of clocks is, first of all, making the laser work better and better and getting that phase diffusion rate smaller. But that's just the beginning. You now have to find a counter. And the trouble is a laser is operating at optical frequencies, which are well above any electronic counters that you could make. So you've got to come up with ways to beat down or divide the frequency of the laser in order to complete the counter. And much of the technology of atomic clocks is about that. It's called frequency cone technology or mode locking technology. But the second problem, so you need to beat that signal down to tens or hundreds of gigahertz so you can count it into various clocks. But secondly, you have to account for the fact that all lasers are built by people and they're not perfect. They're not all the same. They have technical noise, fluctuations and all sorts of weird wonderful things. And so they're all going to be slightly different. But the one thing you can do is make the obvious solution is to try and lock it to a standard where all the frequencies are the same, and that's for atomic transition. So every cesium atom is the same, and there'll be some transition frequency in the cesium atom which is the same for every cesium atom. So you can take all your lasers, build as best you can, but all slightly different, and lock it to a cesium atom and use feedback to stabilize the phase diffusion on the laser. So they're all the steps that go into actually making an atomic clock on a laser. But the fundamental fact is the laser itself is the clock. It's the open dissipator system driven fast from equilibrium that you use to make the counter. Now, I spent a lot of time talking about oscillatory clocks. I just want to spend a few minutes talking about purely random clocks. They sort of have a tick and a tock, but they sort of occur at random relationship one to the other. I'm just going to consider a two-level atom in thermal equilibrium at a heat bath with temperature T, could be pretty hot. And so it's undergoing excitation from the ground to the excited state and spontaneously decaying and stimulated to decay back to the ground state. So it'll eventually, an ensemble of these things will eventually achieve thermodynamic equilibrium. But I'm now going to imagine making measurements of the energy continuously in time on a particular realization. So imagine somehow early that this two-level system could be a trapped ion interacting with a thermal radiation field, and I can make continuous observations of its energy. If I make continuous observations of its energy, that won't change the steady state distribution of the energy. It will still be thermal, still be the standard Boltzmann distribution, but the conditional dynamics will of course look very different. So that the energy measurements themselves, if I just average over all measurement results, won't change thermodynamic equilibrium. But clearly, if I have a particular record of measurements, it won't be in thermodynamic equilibrium. So the simplest way is just rate equations. In that sense, it's not really a quantum clock, it's just a macro process. The quantum disappears because there's this +1 sitting here, which is spontaneous emission, well above If it was a very high temperature, n bar would be so big you could neglect that +1 and just have constant rates of excitation and de-excitation. But n bar is the usual Bose-Einstein distribution. One very important feature of this clock is the ratio of spontaneous emission, which is determined in this rate, to the atomic transition frequency, is the same for every atom, which is the whole point of locking lasers to atoms. That depends on the fine structure constant, the frequency of the transition, the dipole moment, and fundamental physical constants. And beta, of course, is one of those. So that is a universal constant for a given atom. That's important to keep in mind. The observed process is a random telegraph process. It's just ground state, solid state, and sort of switching backwards and forwards at random times. This example is the count, just counting the clock, and you can see that it fluctuates. The period is clearly fluctuating through the random telegraph process. You might think it's not a great clock, but it's actually not too bad. If you take the semi-classical limits, so the temperature is really high, the rates are about the same, and you can just count transitions, and you can just estimate time by taking n and dividing by the rate gamma, which essentially just fixes the minutes. I stressed earlier on that everything is really in count, but if you insist on using SI units, you can divide out divide out by the SI units for the rate gamma, and you'll see it's n over gamma, that's h by omega a on kt. Interesting, you get omega a on gamma, the universal constant I was referring to before coming in. Which means there's a kind of duality of time and temperature in this sort of clock. If I multiply the estimated time by the estimated temperature, it's the same for every atom, and it just depends on n, the number of counts. So every atom has the same omega a, temperature drops out. So these are two experimental parameters. One is the period of the clock based on this, and the other is the thermometer that you're using to determine what the temperature of your bath is. It's one known fact, if you have a good clock, you can make a good thermometer. If you have a good thermometer, you can make a good clock. But now I can look at the uncertainty resulting from that, and I get this very simple result that the fractional uncertainty of the estimated time plus the fractional uncertainty of the estimated temperature is 0, which is a kind of generalized Tolman relation. That is the Tolman relation in general relativity, but here it's just turning up in the fact that we're using a double clock. Probably something important about that for the case of general relativity, but I'm not sure what it is. So here's our thermal clock. We just treat one period as one falling edge to the next falling edge, and you can easily now work out the first passage time distribution of this, and Michael will talk about this, I think, this afternoon. So this is kind of a random clock. It's not so great, but it's not bad. It's pretty good, especially if the rate gamma is large enough for the time, for the kind of events, the rate at which events you're trying to coordinate are occurring. Okay, so we're coming to the end. So let me just quickly talk about the Ravelli thermal time hypothesis. I've essentially already done it. That is it, what I just described. But just to make a connection to what Ravelli said, in general relativity, the problem is figuring out what the time is, because the little t, and also x, y, and z, in the Einstein field equations have no physical significance. What matters is coincidences between physical events. That is, what is a gravitational field where two particles collide, or where a photon is detected, or where a photon is created. They're all the physical events. If you put that time recharacterization invariance into canonical quantum gravity, you discover that the only allowed states are zero eigenstates of the total Hamiltonian, using transforming from the Einstein-Milburn action to the Hamiltonian field, which has often been a bit of a puzzle, but in fact it should be, because if you quantize everything in the universe, what else can it be but an empty eigenstate? The fact that it's zero is a little bit more thought. So where is time? So the point to emphasize is that time is always local. It's all about local coincidence. And what Ravelli emphasizes is, well, let's just look at local thermodynamic equilibrium and ask what can we deduce from that for the passage of time. And sure enough, all clocks are localized subsystems used to coordinate coincidence. And so he just said, well, let's just take local thermodynamic equilibrium and treat it as a clock. Did it in a fairly formal way, and he wrote down the Gibbs-Boltzmann distribution, took the log of the density operator, whatever that means in physical terms, but mathematically that's the Hamiltonian up to this parameter beta, and you can use that to define a flow on the Hilbert space, because the Hamiltonian is a generator of some sort of Lie group, and just treat it as the time flow for the system. And it looks pretty much like what you'd expect for Schrödinger dynamics or irreversible dynamics. Parkman's factor of beta, which is 1 over kt, and so it looks like d tau under this flow defined by this Hamiltonian is beta times dt, which we've got in Smolak called the speed of time. And a lightning way of referring to it myself, given that it's a statistical clock in the first place. So, but the kind of clock I just described, the thermal clock, is an example of such a clock. Here's an example of how you would use it. Let's suppose you have two systems in very different spatial locations, but both in equilibrium with a bath at temperature T, but the local observers don't know that, because they have their local definitions of time and their local definitions of temperature. They don't have to be the same, but let's assume they use the same atom. At least they're all the same. And so the question is, can they set up a communication protocol to establish the fact they're within an equilibrium with a common bath, even though they're very far apart? I'll go through this quickly. You just agree a little protocol where A and B agree that 1 unit of local thermal time corresponds to n transitions in their local thermal clock. You can make that big or small. Better make it big, because then the fluctuations will be smaller. So A waits for NA equals n transitions on her thermal clock, and she sends a signal to B, and I'll neglect time delays for the moment. Upon receiving the signal, B waits for 1 unit of his local thermal clock, that is NA transitions to occur, equals n, and then sends a signal back to A. And between from A sending the signal to B and B sending it back, A records another NA prime transition while all that's going on, while B is waiting for the count to reach n. And so back at A has two numbers, the original count, n sub A, and the new count, n sub A prime, which is the count for sending out the signal and getting it back. And you can show that if they're in global thermodynamic with a global thermal bath, that ratio is equal to 1 plus or minus 1 over root n. So this protocol just establishes locally that both these clocks in non-local places can be in thermodynamic equilibrium with the global bath. And again, you quickly discover there's this simple Tolman-like relation between the estimates of time and temperature A and the estimates of time and temperature B, with no reference to general relativity. They then went on to show that, I'll just mention this because I think it's interesting, you can even work at zero temperature. So the idea is to imagine you have some global field state at T equals 0, but emphasizing the fact that everything is done locally means you can now consider a local quench. So you do something, say a local transpon clock somewhere, and you've got some huge many-body system, and you do a local quench, push it out of thermodynamic equilibrium, and that enables you to use the energy isostatic thermalization hypothesis to back out a way of introducing a local time. The details, I don't know. I'm not sure anybody does, but it would be useful for someone to work it out one day. All right, so I'm coming to an end, so let me just now sort of trail off with some philosophical musings. I apologize to the professional philosophers in the audience, because I'm not that. But I sort of felt obliged at this point in the discussion to try and draw some threads together. And so here's one interesting fact about entropy. Imagine we have a local event, which is a penis just sitting here hitting middle C over and over again, as accurate as they can in a sort of repetitive fashion. And there's a bunch of local clocks, all identical in construction, but all, of course, irreversible and subject to fluctuations, that are counting in the same way I described at the very beginning, when those actual notes sound. So, first of all, you can always set all the clocks so that n equals 1 at the first event. You know, click, and then you let them all go from that point on. Then you can arrange clock coordination. That's essentially what I just said, and that's essentially what UTC is. All the business of coordinating clocks is about trying to coordinate non-local clocks through signaling. And you can agree that two particular events are simultaneous in that protocol. That is, they occur at the same count. Simultaneous means they occur at the same count. But that means the temporal order of any other local event is going to be approximate, because the next time you hit the key of piano C, one clock may count 2, and the other may have still counted 1, or maybe it's counted 3. So they will look non-simultaneous next time. And so there's no way you can achieve that perfect simultaneity with two local clocks unless they are truly identical, because the irreversible fluctuating objects driven by an equilibrium, they can never be. The temporal ordering, likewise, is not fixed. So for one clock, you might order first middle C, second middle C, third middle C, according to some count. But then the probability that the other clock agrees on that ordering gets smaller and smaller as the size of the sequence gets bigger and bigger. And if you plot that, the entropy of that distribution is getting bigger as time goes, as each count goes on. So here I did some simulations taken from a Weyl distribution of a repeating event and the different counts. So they all counted 1 to begin with, but then they all started to differ. And so all these different records here shows the probability distribution is spreading, and therefore the entropy is spreading. And that's based on selecting. But of course you don't have to pre-select, you can post-select. You can say, let's look at all the clocks in the past which just happen to agree here at n equals 1 at that point. There are many, many more trajectories here, but I only selected out all of those which all eventually ended up here. It's like, you know, going to the French Open and looking at all the different players and when they got selected, so that the usual winner, guess who that is, turns up here at n equals 1. So that's post-selection. So you put those together and you get this picture. It increases that way and that way. So the entropy is increasing into both the past and the future in this picture, which is well understood in statistical thermodynamics. But it tends to suggest that the entropy is really a perspectival feature of the agent that's doing the coordination here at n equals 1. And this is a point that Carlo Rovelli has emphasized. It immediately begs the question of whether physical time is related to manifest time, time as we feel it. I'll come back to that. Now, David Albert postulates in his book in 2000 that the universe started in a special low entropy state, called the past hypothesis, and almost everybody agrees that this must be true. But to some extent it's a bit trivial because at that point the whole universe was pre-selected, because that's the only point in the history of the universe where every event was local and coincident, or is by definition. The physical interesting question is, of course, how fast does it increase away from there, and for that we need specific models of quantum gravity. Furthermore, the concept of now is uncertain. Of course, the concept of now in special relativity gets changed. It's not universal. General relativity gets changed again. It depends on the gravitational field. But now it's uncertain. So if we have a bunch of events, A, B, C, Z, and local clock, in which they're all simultaneous, then we say they're happening now. But for any other observer with a different clock, they wouldn't all be happening now. Some will be happening sooner, and some will be happening later, and some will be happening earlier. So now becomes statistical. So all right, so I'm going to finish and wrap up. So I'll just emphasize all clocks are dissipated systems which away from thermodynamic equilibrium. At finite temperature, the fluctuation dissipation theorem limits clock accuracy. At low temperature, quantum noise limits clock accuracy, and that could be measured with back action. And this suggests that probably we can engineer quantum noise, engineer reservoirs, engineer pumping and decay mechanisms to make better and better clocks, other than lasers. And finally, clock irreversibility suggests that physical time is not that different from manifest time. Manifest time is time as it feels to us. It flows, in fact, it flows at a rather erratic rate depending on what you're doing, such as listening to me talking or slow. So let me just come back to the quote I began the talk with. It comes from Douglas Adams' book, The Long Dark Tea Time of the Soul. In the end, it was Sunday afternoons he couldn't cope with. As you stare at the clock, the hands will move relentlessly onto 4 o'clock, and you'll enter the long dark tea time of the soul. So the long dark tea time of the soul is manifest time. And what I've tried to hint at is it may not be very far from physical time. Thank you very much.
So I think we have like 5 minutes for questions. So I think you go first, and then we'll go to Matt.
Me first?
Yeah.
Thank you for the interesting talk. I'm still puzzled by your introduction and conclusion. Don't you think that it's possible to conceive mentally a world where there is motion, there is change, but there is no way to measure it because there is no recurring motion. There is never cycles anywhere. It's only motion forward.
Yeah, that would be thermodynamic equilibrium.
Sorry, so just this I'm
Yep.
typing a lot. My
Sorry.
thoughts is that if this is possible, then it would mean that you could still differentiate between 2 changes. So you can see that you can see that 2 changes can be exactly the same in amount of change and type of change and everything, but still be differentiated by duration. So it would mean that change is not time, and it would also mean that time is not the measure of time. So I think it's still interesting to differentiate between these 3 concepts: the measure of time, and change.
Yes, I completely agree. So the connection between time and change is very subtle. Now, the case you mentioned where nothing recurs would happen if the whole universe was in thermodynamic equilibrium and everything in it was in thermodynamic equilibrium. But now we have to ask ourselves, what would it even mean for an agent to coordinate change through clocks and events? And so every time I think about this, I'm always pushed right back to what is a physical agent and how do they learn the laws of physics. And now it gets difficult because you have to envision some sort of machine, which by definition is not in thermodynamic equilibrium, otherwise it's not an agent. It has to be able to observe the world.
Why do you say it would have to be in thermodynamic equilibrium? It could still be, there could still be chaos and all kinds of stuff, just not
Yes.
occurring.
But there can't be an agent if it's in thermodynamic equilibrium. I'm just stating that boldly. There can be no machine for which clocks are relevant if the whole universe is in thermodynamic equilibrium.
Well, that's because we are in our picture. It's totally conceivable that there could be other kinds of life where there's no need for, heating hearts or anything.
Oh, absolutely. I agree. In fact, the whole point of this discussion is that clocks are physical systems and learning agents will also be physical systems, and they can operate on wildly different physical principles from us. They could have limit cycles not based on certain sorts of electrochemical oscillators in the heart, but based on, I don't know, tunneling properties in neutron stars or something. They could be operating on timescales of millions of years instead of milliseconds like us. Yeah, so I don't disagree with that at all. But nonetheless, in order to talk about time at all and change, I cannot see how you can avoid introducing a learning machine for a learning agent. Now, you may disagree with that. In fact, a lot of people do disagree with me, but at the moment, that's where I'm stuck. And so you're forced to go and look at books on neuroscience, and you can discover, well, there's not many clocks in the brain either. They're all just doing their own thing for whatever reason they need to do. But there are mechanisms to coordinate them across the circuits of the brain. And it's much worse than that. Space is the same. Once you take this picture of time, space also vanishes from the picture of something physically out there. It's something that we use in our brains to coordinate experience, just like time.
What do you think happens?
Sorry, can I interrupt? I think we should move on to the next question. It's a very interesting discussion, but maybe we move it to the lunch break. Sorry,
Sure.
guys, but I want Max to have a chance to ask his question as well.
Oh,
really?
So with this example here, it's very interesting example of the like laser clock, the topic effectively is that removed. Naively, classically speaking, I would think that you discussed the question of what should be measured, what should be observable. Naively, classically, I would say the phase, because it's one complete cycle of phase that gives you one ticking effectively. But in the model of it, you modeled it as intensity. So but I mean, I understand, like, what is the phase? It's the changing intensity.
No, I modeled it as Hamilton detection, which is in effect, it's the only phase measurement you can make in quantum optics, is Hamilton electron detection.
But
You can't measure phase directly in quantum optics, because no one's figured out how to do it. But if you measure the electric field, you'll see it oscillate. But if you measure the intensity, you won't.
But the terms in there were induced almost by incohering the number of bits. Or maybe I misunderstood.
No, okay, so I did go through that very quickly. So the point is, when you're on the limit cycle, that complicated Marshall equation I wrote down simplifies dramatically to something that only has that double commutator with A dagger A. So on the limit cycle, as far as all the noise is concerned, it just looks like phase diffusion. And that's coming from spontaneous emission, ultimately, in the system. But on the limit cycle, it just appears as phase diffusion, leading to the Charlotte-Towns line. So that's the noise mechanism in the laser above threshold. The next step is to ask, what do you measure, and what does the conditional dynamics look like? Then you add this additional nonlinear term to describe conditional evolution of the system, given the record of observations of the phase. I did go through it quite quickly, so I simplified it if you didn't follow all the steps. But if you look at those papers by Howard Wiseman, I think he has a very clear discussion of each step as it emerges.
Okay, so I think with that, just find let's thank Gerard again.